Okay, so now the subject for today will be about functions of several variables. The idea is that if you have an interval on the in the real line, then a function defined on I taking values in R, it's a function of one single variable, f of x, and we have a formula. It's, for example, x square root of x squared plus 7. This is a function of one single variable. Now, what's the idea of functions of several variables? 2, 3, and so on. For this, we need to have something similar to the set of real numbers. So that is the space R at n, which means the Cartesian product of R with itself n times. An element here is written as x1, xn with xj real numbers. Now, the usual particular cases are when n equals 2. Here, and the elements are denoted by xy instead of x1, x2. And when n equals 3, we have the elements are x, y, z. Now, from linear algebra, we know that this is a so-called linear space. I shall not enter into details about linear spaces, but we shall use some elementary facts about them. Anyway, we can add vectors. The elements of R at n are called points or vectors. The sum of two vectors is given by the addition of the corresponding positions and the multiplication with numbers, scalars or numbers, is the same. So alpha times a vector, it means to multiply each component of the vector with the scalar alpha. With these two operations, R at n has a structure, special structure, which is called a linear space. And the exact definition you have in linear algebra. We shall use this. Now, the basic fact here is that if x is an element in R at n, its norm, the norm of x, is given by the following expression, is the square root of the sum of the squares of its components. And it represents, for example, if we are in the plane, if this is the point of coordinates xy, then root of x squared plus y squared, it's exactly the distance from the origin to this point. We know from elementary geometry, yes? So actually, this is the distance from this 0. 0 means the vector of components 0 to x, which is x1, xn. Now, in general, the distance between two arbitrary points, if this is x of components x1, xn, and this is y of components y1, yn, the length of the segment from x to y, so the distance will be given as the norm of the subtraction x minus y, which means this. So this is the distance between the vectors x and y. X all the time is x1, xn, y it's as in the picture, yes? So the distance between this, for example, if we are in, for n equals 2, the distance between the point xy and the point uv will be the norm of xy minus yv, which means the norm of the vector x minus u, y minus v, which means the square root of x minus u squared plus y minus v squared. Something similar holds in 3 dimensions. If n equals 3, I don't write it anymore. Now, the use of this distance is the same as the use of the distance between real numbers. Remember, if we have 2 real numbers, then the distance between them is the module of x minus y. So the norm is something similar to the module, and if we have this, we have the possibility to evaluate the distance between points in R at n. Consequently, we have here some interesting sets, such as disks. If A it's an element in R at n, and if R it's a positive number, then the disk of center A and radius R is the set of all points in R at n, with the fact that the norm, with the property that the norm from A of x minus A, it's less than R. In the plane, this is indeed a disk. If this is A and this is the radius, then this is called the open disk. The closed disk, it is when we put here less or equal. Yes, that includes the circle. Okay. Now the use of the disk is similar to the use of centered interval at some point. Here it's in the set of real numbers. If A it's a number and epsilon it's a positive number, then the interval A minus epsilon A plus epsilon is actually the disk of center A and radius epsilon. Yes, the fact that x belongs to this interval is equivalent with the fact that modulo of x minus A it's less than epsilon. So this is exactly the definition of the disk. In the plane we have disks. Yes. In the space we have spheres, actually what is inside the sphere. Okay, and now we can write almost everything from calculus on the set of, on the real line here by using the norm. This is the idea. So first, the basic notion in calculus, it's that of a convergent sequence. What that means? Well, first of all, what is a sequence? Or sequence of vectors? A sequence means a function defined on the set of natural numbers taking values in R at n. So if you apply f to some k, we shall obtain here a set of sequences of real numbers. The first, we need to write with 2 indexes, one for k and one the position. Let's say 1 x1 k, x2 k, and so on, x n k. Every x k j is a sequence of real numbers. For example, a sequence of 2-dimensional vectors is the following: xn, yn, k. Let's put it with k. Here we can put n. Attention, n here is occupied because of the dimension, but here we can write n. The usual examples and exercises will be in n equals 2 and n equals 3, so we don't need a general n. For example, what I'm writing now, it's a sequence of 2-dimensional vectors. Yes. Each component, actually, it's a sequence of real numbers. If somebody, for example, asks you, what do you think is the limit of this sequence? What would be your answer?
The point E.
To E and 0, maybe. Well, the answer is right, but it's curious because for the moment, we didn't define yet what a convergent sequence of vectors means. You understand? So we don't have a definition, but we can recognize if a sequence of vectors is convergent. This we will discuss this later. For example, when n equals 3, a sequence in the 3-dimensional space could be, for example, this one. If somebody asks you, look, what do you think is the limit of this sequence of vectors? What would you say?
E0 and
E0 and 0. Yes, something like this. Okay, so convergent sequences seems to be very natural. I shall not give now the definition, but I shall just say that a sequence of vectors is said to be convergent if and only if each of its components, it's a convergent sequence of numbers. That is not the definition, it's a characterization, but this is the most useful in exercises. So let's write it in 2 dimensions. Xn, Yn is convergent as a sequence in the 2-dimensional space R at 2, if and only if both Xn and Yn are convergent, of course, in the set of real numbers. Moreover, if Xn tends to A and Yn tends to B, then, of course, the sequence Xn, Yn will tend to the vector AB. So everything is on components. This is the keyword, on components. We look to every component, we see a sequence, and if all these sequences are convergent in the set of real numbers, then our sequence of vectors will be convergent in the n-dimensional space. Okay, I repeat, tomorrow we shall see the definition, but now just this characterization. Okay, so now if we have the notion of a convergent sequence, we can discuss about limits of functions and so on. For example, now let's discuss now about functions. This is our goal, actually. Now, what a function of several variable means? Well, it means this. We have a subset in R at n, and a function of n variables. It's a map from D, which could be also the entire R at n, taking values in R at m. Such a function applies to an n-dimensional vector, because here we are in R at n, as you see. And the result is a vector of m components. So it's something of the following type: f1 of x1, xn, f2 of x1, xn, and so on up to fm of x1, xn. Every f1, f2, and so on, fm are called the components of capital F. The components of capital F, and each of them is a function from D, but taking values where? In the set of real numbers. Yes, so f1, fn, fm are all functions of n variables, but taking values real numbers. Okay, let's see some examples. For example, a function f defined on R squared taking values in R at 3 looks like this: f of x and y equals 1 over root of x squared plus y squared plus 1, e at x squared minus y, and the last component, let's say, root of x squared plus y at 4. This is a function of 2 variables, x and y, taking values vectors of dimension 3. It has 3 components. In our previous notations, this is F1, this is F2, and this is F3. Each of them, it's a function of 2 variables, but it takes values, numbers, not vectors. Okay. This is our object of study. Yes. Of course, now we need to define what it means for such a function, the notion of limit. We can define it by using vectors. We say, for example, that the limit when x tends to a of f of x, here attention, x, it's a vector x1, xn, a, it's a vector a1, an, and f of x is a function as before. We say that this is the limit is here, it's L, which is an element in R at M. If and only if we characterize this with sequences. For every sequence xk from the domain of definition, the sequence f of xk tends, when k tends to infinity, to L. So in this moment, if we know what a convergent sequence means, we can define limits of functions. Okay. And we have also here continuity, what it means for a function to be continuous. F is continuous at the point A if the limit at A of f equals the value of f at A. In general, it could be a limit, which if it is always at every point it satisfies this condition, then we say that f is simply continuous. It means continuous at every point. We shall work only with continuous functions. So we will not be interested in how to study the continuity to compute limits of functions of several variables, because our main goal is to use the derivatives in order to find the basic properties of functions. That means calculus. Calculus means to study functions with derivatives and with integrals. The first semester is differential calculus, so using derivatives. The second semester will be integral calculus, so we shall use mainly integrals. Okay, so now we want to introduce the notion of partial derivatives. We shall do it now. So now let's discuss about partial derivatives and then try to compute partial derivatives. Let's consider the functions of several variables, but taking values numbers, because if it takes values vectors, we shall deal on components. So our object is a function defined on D, taking values in the set of real numbers, and D, it's a subset of R at N. So F applies to x1, xn, and the result is a number. Particular cases, when n equals 2, we have f of x and y. When n equals 3, we have f of x, y, and z. Okay. Now, at the lecture, we shall see how we arrive at the notion of partial derivatives. Anyway, the function, for example, let's take a function of 2 variables, f of x and y, and let's fix a point A, B in the domain of definition. What we would like to know? Well, we are interested in problems of the following type. Here is the point AB, and the function f is defined around this point. And now, you see, we are at AB. So the function takes the value f of AB. And now we move a little bit around the point AB. That means we change from AB to some xy. The values of the function have a variation, which is given by f of x and y minus f of f minus f of ab. And now we would like to have a measure of the speed of how quickly the values of the function are changing when xy is moving from AB to some close point xy. So that what in terms of calculus say the local behavior of the function around this point. How quickly the values of the function are changing when we are moving not far, rather close to the point AB. For functions of one single variable, we have a measure that is the derivative of f at a. If this number is, for example, positive and very large, then the function is increasing very quickly around the point A. If this number is negative, then the function is decreasing around the point A, and so on. When this number is 0, it's like the function, it's like a constant function around the point A. Well, we need something similar for functions of two variables and more general for functions of several variables. Okay, this is the idea. And now the idea is the following. Like many other problems in many variables, we shall look to the problem in the following way. To see what happens on directions which are, for example, parallel with the axis of coordinates. So we shall consider the following situation. So we are here, we are at the point AB, and now xy is moving around AB, but it is moving in the following particular way. It is moving like this. What that means? It means that y is constant, b. In that moment, our function, it's a function of one single variable, which associates to x the number of f of x and b. This is the function of one single variable. We know a measure for how quickly the values of this function are changing around the point A. Yes? It's the usual derivative because, attention, this is a function of one single variable. The derivative of this function at the point A is given by the following definition that you are very familiar with. Limit when x tends to A of f of x and b minus f of a and b over x minus a. This is a limit of a function of one single variable, like in the college, nothing new. Okay, so the value of this limit, it's a measure of how quickly the values of f are changing if the argument xy is moving like this, in this very particular way. That means y constant. Similarly, if the point xy is moving like that around the point AB, that means this time x is constant, a, and we consider the function of one single variable y going to f of a and y. For this function of one single variable, we must consider its derivative as a function of one single variable, which is given by this limit. Okay. Again, this number, it's if it exists and it's finite, it's a measure of how quickly the values of the function f are changing when the argument is moving like this. Well, we shall see later that if we have these informations, we can somehow recuperate the behavior of the function as a if the point xy is moving in a general way around the point AB. So the idea is that if we are looking on the projection, it's enough. This is it. And now these two numbers are called the partial derivatives of the function f at the point AB. more precise, this is the partial derivative with respect to x. This is the part with respect to the variable x. And this is the partial derivative of f with respect to the variable y. With respect to y at the point AB. And there are numbers. Well, okay. Of course, in three variables, we shall have three. I shall just write, and this is, I will be over with the theory. For example, for a function of three variables, it has three partial derivatives at some point ABC. For example, the partial derivative with respect to x will be limit when x tends to a from, here we have x minus n, here we have f of x bc minus f of a bc. So we fix the variables y and z, we give them constant values b and c, and now here we have a function of one single variable x and so this is the partial derivative with respect to the variable x. Okay, now the partial derivatives have some special notation. The partial derivative with respect to the variable x, it is denoted by der on def to der on dex at the fixed point we are talking about. This symbol is called d round, so round d. It's a sort of the letter d, but round. So it's the notation, the general notation for partial derivatives. We have the partial derivative of f at the point x, at the point with respect to the variable x. For example, if I want to compute, let's take a function f of x and y, let it be x squared y. Okay, and let's consider the point AB equal to, let's say, 1, 1, or 1 minus 1. And we want to see the partial derivative of f with respect to x at the point 1 minus 1, and with respect to y at the point 1 minus 1. According to the definition, that is limit when x tends to 1 of f of x and minus 1 minus f of 1 minus 1 over x minus 1. This is according to the definition. And now we need to compute this limit, which is rather simple, must be. It's like a limit of a function of one single variable. So here f of x and minus 1, it means x squared times minus 1, so that is minus x squared. F of 1 minus and minus 1, it is minus 1, so plus 1. And this limit, which is 0 over 0, can be simplified by x minus 1, yes. So here we simplify by we need to change the sign, yes, of course. So I shall put here plus plus. Okay, so that is 2. So the partial derivative should be minus 2, yes. Just 1 second. It must be
1 minus 6.
1 minus, let's see. So we have limit when x tends to 1 to minus x. Okay, let's put the sign here. Like this, yes. So now we have minus x minus 1 times x plus 1 over x minus 1. And we have, of course, minus 2. So the partial derivative of this function with respect to the variable x at the point 1 minus 1 is minus 2. We compute it by using the definition. The other one, similarly, will be limit when y tends to minus 1 of f of 1 and y minus f of 1 and minus 1 over y minus minus 1, so y plus 1, which means f of 1 and y. It means we put here x equals 1, we get y minus f of 1, and it's minus 1. And below we have y plus 1, which gives us 1. No? So the partial derivative of the function f written here with respect to the variable y at the point 1 minus 1 will be 1. How we computed them? By using the definition. But in the college, you remember, we don't compute derivatives by using the definition, of course. We have some rules of differentiation for functions of one single variable. Okay, those rules, now if we think a little bit to the definitions of the partial derivatives, we understand that we can apply those rules, but in an appropriate way. Actually, how we compute here the partial derivative, what it means according to the partial derivative of the function f with respect to x. Actually, all the other variables are constant. For instance, the variable y, you see it's constant. And it's like we have a function of one single variable, and we compute its derivative. So, consequently, so you can put a title, computing partial derivatives by using the rules of differentiation. For this function, if we want to compute the partial derivative with respect to x at some arbitrary point, I shall write like this. But usually I don't write anymore an arbitrary point, unless it is a particular one like here. Yes, here we compute it like as follows. We think to this expression as a function of one single variable x, because attention, y it's a constant. So y it's a constant, x is the only variable. And now, what's the derivative of this expression with respect to x as a function of one single variable x? Of course, it is 2xy. On the other hand, derondef to derondoi of x and y, if we think to this expression as a function of one single variable y, x being a constant, then the derivative of this one will be, according to the usual rules of differential, will be x squared. In particular, if we want to compute the derivative with respect to x at the point 1 minus 1, we get minus 2 from here. And the partial derivative of f at the same point with respect to y will be 1. Exactly the same values, of course, we obtain here in this by using the definition. But the usual way we shall do it is by using the usual rules of differentiation for functions of one single variable. Because here what we are doing is to differentiate functions of one single variable. And now let's do some exercises in this. If you have some questions about this very short theory, actually, I try to explain several things, but now we shall focus on the computation of partial derivatives. That will be the main goal, but if you have any question until now. Okay, let's make some computations. For example, consider the function f of x, y, and z equal x times x squared plus y squared plus z squared. And let's compute the partial derivatives of this function at some arbitrary point. Namely, derondef to derond x, derondef to derond y, and derondef to derond z. Again, derondef to derond x means this. In this expression here, y and z are constant. And the only variable is x. And we compute the derivative of the function of one single variable which associates to x, x square root of x squared plus y squared plus z squared. Here y squared and z squared are constants. Yes, in this moment things are clear. We are using the usual rules from the college. In this case, we have a product. Yes, so the derivative with respect to x will be the derivative of x, which is 1 times x squared plus y squared plus z squared, plus x, not derivated, times the derivative of this expression with respect to x. That is 1 over 2 root of x squared plus y squared plus z squared, times the derivative of x squared plus y squared plus z squared with respect to x. What's the derivative of x squared plus y squared plus z squared with respect to x? The y and z are constants. It is
2x.
2x, of course. So we've got the result. Of course, we must put it in a simpler form as usual, but this is very simple. Yes, so it will be root plus x squared over the root 1 can also here make that. Now, the derivative with respect to y. X is a constant here in front. So it goes out. It is x times, here we have 2y over 2 root of x squared plus y squared plus z squared, which means actually xy over the root. Similarly, with respect to z, we shall have x is a constant times, here we have 2z over 2 times the root, which means xz over the root. Okay, let's see another example. F of x and y equals, let's say, x squared times e at x minus y at 3. This is a function of two variables. Let's compute the partial derivatives with respect to x. So we have a product that is 2x times e at x minus y at y minus 3, y at 3, plus x squared as it is, times the derivative of, with respect to x, of the exponential. That will be e at x minus y at 3, times the derivative of the expression x minus y at 3 with respect to x, which is
1.
1. So we get 2x plus x squared times e at x minus y at 3. Let's see what happens when we differentiate with respect to y at some arbitrary point xy. Now x squared is constant, times what? E at x minus y at 3 times what?
Minus 3y squared.
Minus 3y squared, very well. So that is minus 3x squared y squared e at x minus y at 3. Okay. So computing partial derivatives, which is the main goal in the beginning here at the study of functions of several values, I think it's clear. Now, but we can go further and let's see the following situation. Suppose we have a function of 3 variables, f of x, y, and z. It has 3 partial derivatives, but attention, we look to these partial derivatives as functions, like here. You see, here I didn't compute the partial derivative with respect to x at some particular point. Now we can do it if we want, because we have the general expression. So now what I'm trying to say is that the partial derivatives are actually functions exactly like the function from the beginning. Each of them is a function of 3 variables. It applies to x, y, z. If the initial function was a function of 3 variables, yes? Okay, so we are in the same case as in the beginning, a function of 3 variables. We can consider its partial derivatives. For example, this function, this one, has how many partial derivatives? 3, of course, because it has 3 variables. We may consider the partial derivative with respect to x of der on f to der on x. We can consider the partial derivative with respect to y of the function der on f to der on x, and the partial derivative with respect to z. I shall explain the notation of der on f to der on x. So only this one has, of course, 3 partial derivatives because it is a function of 3 variables. With respect to x, we shall denote like this, with der on f to der on x. That means consider the partial derivative with respect to x of what's written here, of this function. Here, the partial derivative with respect to y of this function, and so on. Okay. There are some special notations for this partial derivatives. Instead to denote like this, but this is the definition. It shows what it means. This is denoted with in the following way. We put here a 2. That means I intend to differentiate f 2 times. With respect to what variables? Here in the first case, it was first we differentiate with respect to x, and then again with the same variable. Well, instead to write like this, here, when the variable is the same, the usual notation, it's a convention. It is like this, der on x squared. So that means the meaning of this is the following. You have a function of several variables, differentiated 2 times with respect to the same variable, namely x. This one will be der on to f. That means we intend to differentiate f 2 times. With respect to what variables? First, with respect to x, we are looking here. First, it was with respect to x, and then with respect to y. This one will be denoted like this. Yes, attention to the order of the variables. So, yes. Similarly, this one has 3 partial derivatives. For example, the first one will be to differentiate with respect to y, yes, with respect to x, sorry. Yes, der on f to der on y. That will be denoted how? Der on to f, that means we differentiate f 2 times with respect to what variables? Attention to the order, which is written here. First with respect to y, and then with respect to x, and so on. These partial derivatives are called second order partial derivatives. And we can continue, of course, but the usual problems in calculus are solved by using the first order. These are called now first order partial derivatives, or simply partial derivatives. And now, by using first and second order partial derivatives, this looks like the study of functions of one single variable when the first derivative and the second derivative were enough in most cases to understand the behavior of the function. Something similar holds here. The first order and second order partial derivatives will be enough in most cases to decide the behavior of the function f around a fixed point. So these are second order partial derivatives. For example, a function of 2 variables has how many second order partial derivatives? We have 2 partial derivatives of the first order, and now each of them has 2 partial derivatives, which will be denoted with this, like this. Attention what that means. Here we differentiate first with x, and the result, which is this one, will be differentiated with respect to the other variable y. Here, we first differentiate with respect to y, and the result will be differentiated with respect to x. And here, the last one, it is this one. You see, these two here are so-called mixed second order partial derivatives. Why mixed? Simply because we have both variables. Yes. These are not mixed because here we differentiate 2 times with respect to the same variable, and here, yes, we mixed the variables. You see, if we now look to these two functions, they are obtained in the following way. We have the function f from the beginning, and we differentiate it 2 times, but in different ways. Here, we differentiate it with respect to x, and then the result will be differentiated with respect to y. Here, we are doing almost the same, but the order is different. We first differentiate with respect to y, and then the result with respect to x. And now I put you a question. What do you think? Does the order matters? In other terms, are these two functions equal or not? What do you think? What do you expect?
They are equal because we can interchange the limits. So
They are not always equal.
Well, you gave 2 different answers. The first one was yes, because we have some commutation. Now, actually, we don't study and compute limits of functions of several variables because this is a technique, not very complicated. In the books I put on the Microsoft Teams and the Moodle platform, there are a lot of solved exercises, but we are not interested in that kind of exercises because we have many other more important things to do. Well, but actually, when you compute limits of functions of several variables, the idea to change the order, it's false. You see, and if I understand correctly what you are trying to say, you think something like that when xy tends to ab, yes, we have a function. You think maybe you think like this is limit when x tends to a from limit when y tends to b of fx x and y, something like this. I think you thought to something like this. Yes, is it correct what I am trying to say?
yes, that's correct.
Well, this is not correct. In general, these 2 limits are not equal, and also it's not equal with this one. So the idea to change the order to consider these are called iterated limits. The iterated limits are not the limit in R squared. So this argument, it's not valid. Yes, okay. However, there is a strange final about this. Let's take an example. Let's take a function of 2 variables. Let's compute the mixed partial derivatives and try to get some conclusion. Let's take a function which is far away from to have some symmetries between x and y. You understand what I am trying to say. For example, let's take something like this. X squared e at, I don't know, x minus y squared. You see, this function is far away to have a symmetry, something between x and y. Yes? Okay. So we need to compute the second order mixed partial derivatives. These two. Not all the second order partial derivatives. We don't need to do that and compare them and try to guess something, to make a guess. Of course, first we need to compute the first order partial derivatives. We have a little bit to work here, but it's worth. Let's check again. Okay, so this is the partial derivative with respect to x. Now let's see the partial derivative with respect to y, which will be minus 2x squared y e at x minus y squared. X squared is a constant, the exponential times the derivative of x minus y squared with respect to y, which is minus 2y. Okay. Did you get the same?
Yes.
Yes.
Okay. Yes. Take it easy, don't hurry. You are in the beginning now, but let's see, let's check everything. Now let's compute the second order partial derivatives. For instance, there on 2f over there on the y, there on the x, this one. It means to differentiate with respect to y, there on f to there on x. That means differentiate with respect to y, this one. And now let's see what we get. Now 2x plus squared, x squared is of course a constant. So that will be times minus 2y e at x minus y squared. Okay, we can write 2 minus 2 times xy plus x squared y e at x minus y squared if I made the multiplications. Now let's see there on f to there on x, there on the y. That means to differentiate with respect to x, there on f to there on the y. I shall not write it anymore, it is here. So we need to differentiate this one with respect to x, attention. Yes? Okay. So here we have a product. So it will be minus 4xy times. Here I missed something because here it's 2xy. Yes. Attention. Here it's 2xy. Yes. Because it's this one. 2xy plus x squared y. Okay. Let's go back here. So it's minus 2x minus 4xy times e at x minus y squared minus 2x squared y times e at x minus y squared and times 1 because the derivative with respect to x is one of the expression. Okay, so we get minus 2 times 2xy plus x squared y times e at x minus y squared, and somehow at the first sight, strangely, we've got the same value. Well, it's not a coincidence, of course, because this function is far away to have special properties of symmetry between x and y. On the contrary. So it seems that the second order mixed partial derivatives are equal. Well, actually, this result is not always true, but we shall work. We will see at the lecture in the theory. We shall work only with functions with this property. This is true if the partial derivatives of the second order are continuous, and for us the usual functions have this property. So that's not. So usually they are equal. So for us, we shall work only with this kind of functions, which are very general. So the order of differentiation doesn't matter. This is the conclusion. Yes. This has a name. It's called Schwarz symmetry theorem. So the symmetry theorem about the second order partial derivatives. It's a little bit of surprise here, but because, attention, the argument with the commuting limits doesn't work. This is that's why it's maybe a little, but however, the definition, the proof goes well, despite the fact that we cannot commute the limits there. I understood your argument. Okay. So, for example, for a function of two variables, if we want to compute the second order partial derivatives, we need to compute only three. The not mixed, these are the not mixed, and one mixed. Doesn't matter which one, because they are equal. Yes. Of course, this works for an arbitrary number of variables. Okay, let's see an exercise, a classical one. Consider the function. Okay, tell me, you want to make a break, you want to continue and to stop at some moment. Tell me when do you want to stop the lesson, yes? Let's consider this function. No, okay. No, let's start with something simpler. Let's consider a function of two variables. Logarithm of x squared plus y squared. And the question is to compute the following expression. The sum of the two second order partial derivatives, but the not mixed. See? This expression in general is called the Laplacian of the function f. In general, if f is a function of n variables, the Laplacian, which is usually denoted with a Greek symbol delta, capital delta, delta f, it is the Laplacian, means the sum of the second order partial derivatives, but not mixed. That's a definition, nothing. Well, it's the Laplacian plays an important role in calculus. But for us, for the moment, we need to know what it means and how to compute it. For example, for a function of two variables, the Laplacian equals this expression. Okay, and we want to compute it. Please compute the Laplacian of this function and tell me the result you got. I shall make also myself the computations. Of course, we need first to compute the first order partial derivatives. Which are given by these simple expressions. So the partial derivative with respect to x will be 2x over x squared plus y squared, while that with respect to y will be 2y over x squared plus y squared. Of course, there is a sort of symmetry here because the function itself had some symmetries here. Yes, if you replace x by y and y by x, you get the same function. So it is expected to have some symmetry here. Now let's compute the second order not mixed partial derivatives, because for the Laplacian we don't need the mixed ones. We can compute also the mixed, but that is not our goal. Okay, so we need to take this function and differentiate it with respect to x. Of course, this is a ratio. We shall use the formula to compute the derivative of. Attention, here x is the only variable, y is a constant. So it will be 2x squared plus 2y squared, and then minus 4x squared. So that means 2y squared minus 2x squared over x squared plus y squared squared. And now the other one, there on to f over there on y squared, which means to differentiate with respect to y over x squared plus y squared. That means
because of the symmetry,
because of the symmetry, it is expected what we get. Let's compute it, however. So we get, of course, 2x squared minus 2y squared over x squared plus y squared squared. And now, what's the Laplacian?
It will be 0.
The Laplacian is 0. That is an interesting result because functions which have the Laplacian 0 are important functions in calculus. They are called harmonic functions. So a function with the property that its Laplacian is 0 is called, then f is called a harmonic function. And the study of harmonic functions, it's important. It started with the German mathematician Gauss and continued because they are important. For instance, in the study, you'll see in the second year, you'll use harmonic functions on complex analysis, in the study of some equations with partial derivatives as they appear. Okay, and this is an example of an harmonic function of two variables. Of course, if we want, we can compute also the mixed partial derivative. Let's do it because maybe it's useful to have, it has nothing to do with the Laplacian. Attention, we can compute it in two ways. Differentiate this one with respect to y, or differentiate this one with respect to x. The theory says we get the same. So, okay, let's differentiate this one with respect to x. Doesn't matter. 2y is a constant, so it's minus 2y times the derivative with respect to x of this one, which is 2x. So that will be minus 4xy over x squared plus y squared here. Of course, that the two partial derivatives, the mixed one, are equal here. In this case, it is expected because of the symmetry, of initial symmetry of the function, but that is true always. Now, well, we have an example of a function in two variables, which is harmonic. Okay. And now let's see another exercise. I will clean up the whiteboard. Okay. Let's consider the function of three variables, fx, x, y, z, 1 over root of x squared plus y squared plus z squared. This is a function of three variables. It also has some symmetries here, of course. And the question is the same, compute the Laplacian. And let's see if we can reduce the computation as much as possible because of the symmetry Maybe. Anyway, the partial derivative with respect to x. Attention, we can do it in many ways, as a ratio, or you can write f as x squared plus y squared plus z squared at -1/2 and compute its derivative as a power. Yes? How do you prefer?
As a power.
So you want to use this form, yes?
Yes.
Okay. So we shall differentiate on this one. Maybe it's good to do it then again by using this form, and also, of course, observe that we get the same. Okay, so we differentiate here with respect to x. I think we get this. Okay. Is it okay? Did you get the same?
Yes.
Now, can you tell me directly the partial derivative with respect to y and with respect to z? Because of the symmetries between x, y, and z. Minus y times x squared plus y squared plus z squared at -3/2, and minus z times the same. Okay, these are the first order partial derivatives. Yes? In order to compute the Laplacian, we need to compute the second order not mixed partial derivatives. For example, there on 2f over there on dx squared, and maybe it will be enough, because maybe the other maybe we shall try to write them directly if we can. Okay, let's see. So we need to derivate with respect to x this expression, which is a product. Yes. Here we simplify by 2, and we get plus x 3x squared, yes, times x squared plus y squared plus z squared at -5/2. This is, please compute and check if you get the same result.
Yes, I got the.
Please.
I got the same result.
Okay, so the second order partial derivative with respect to x, this was written here. Can we now write the other two directly? By symmetry means.
Instead of 3x.
Here there will be 3y squared, of course. They don't look very good. Rather complicated, but okay. And now the Laplacian of f will be the sum of these three expressions. Please make the sum.
Is equal to
The result is 0. Yes. I made a computation here because here the power is 1 plus minus 5/2. It is exactly minus 3/2. This is with minus, this is with plus, and they vanish. Okay, so this is again a harmonic function. Here you have an example of a harmonic function in 3 variables. They don't look at all similar, those in 2 variables with those in 3 variables. Yes. So please again.
the function is harmonic because of the symmetry.
Yes, harmonic functions have a symmetry always in the variables. Yes. And that symmetry is somehow related to the norm of the vector of coordinates x1, xn in R at n, which is root of x1 squared plus x2 squared. You see, in this function, we have the expression all the time, x squared plus y squared in 2 variables, x squared plus y squared plus z squared in 3 variables. So the symmetry is somehow related to this expression, which is itself symmetric in these variables. Yes? Okay. If you have any question, please, about what we discussed now, or other kind of questions from the previous subjects. So now the next steps will be to understand the topology of R. Topology means the structure of R at n regarding limits of sequences and limits of functions. Yes, this is what we are going to do at the lecture. And then the technical part is to compute partial derivatives. The use of the partial derivatives will be, of course, that we will be able to study the basic properties of the functions of several variables, mainly the local extrema. Yes. Okay, I shall stop now the record.